Hi, welcome everyone to Lecture 2 for ANOVA. This is the ECO3411 Lecture 2, and it's on a two-way ANOVA. Let me just go back and quickly review what we covered last time, just to kind of get us up to speed here. For the most part, what we learned is we learned how to run a one-way ANOVA, how to read the table, realize that the F computed is actually a ratio of variances, the variance between groups compared to the variance within groups. If the variance between groups is very large, then your F computed is going to be large, and then you reject H naught and you conclude significantly that the means differ. If the variance between groups is much larger, then you can conclude, yes, the means differ. And so there's my F computed. We learned how to run it in Minitab, how to put the data in Minitab, and then also how to run a completed hypothesis test and where to look for data about that hypothesis test, as well as doing summary and implications. So now we're down at homework 1. We did a virtual exercise. All right, let's talk about the test. The underlying assumptions are as follows. We have to have these assumptions hold in order for the ANOVA to be valid. There must be a simple random sample taken for each treatment group. So basically within each airline, a random sample of satisfaction is taken. So we take a random sample of people. We can't just take young people. We just can't take old people. We can't take crabby people. We've got to take a random sample of the population as a whole, so then we can infer information about the whole population. So the sample has to be random. And then within each treatment group, say within each airline, the observations are normally distributed with different means but the same variances. We can't have one airline with huge variance of their outcome measures and one that are really tight variance, because then we could be confusing the between group versus within group. Kind of makes sense? That's why I was just talking about that a minute ago. So within each treatment group, we have to have the same variances in order for the ANOVA results to be valid. How do we test this? We do a test for equal variances with this assumption. So in our test for equal variances, basically we are going to go to, get to Minitab. We're going to go to Stat ANOVA one way, Stat ANOVA one way. And then it's not that. It'll be Stat ANOVA. I found it. Ready? Stat ANOVA. Test for equal variances. Yay! It's right down here. Stat ANOVA, test for equal variances. And then basically you're going to do the same thing. Response data are in separate columns, and then you put in the response variables, and then you say OK. So everybody get that? So in order to do the test for equal variances, we're going to put those data in here. And then we'll go to Stat ANOVA. Instead of one way, we're going to go right down here to test for equal variances. Good? All right. So what we're going to get when we do the Stat ANOVA test for equal variances, okay, we're going to put those data in here, and we're going to call up these data here. The output that we're going to get is test for equal variances among these groups, right? The method, null hypothesis, all variances are equal. At least one variance is different. We're going to use an alpha of 0.05. So here what we have are the results of the test. These are the test statistics that we're going to use in a new hypothesis test. Our new hypothesis test, similar to our ANOVA, will have an H naught, an HA, an F computed, an F table, and a statistical conclusion. So we need to figure out where are we going to get these test statistics. Well, when we run the Minitab test for equal variances, out will pop our test statistic. We're going to be using the Levine's test for this. Levine's test for equal variances. So we're going to get my F computed, which is right here, and then the p-value associated with that test. Does everybody see where we're going to get that? We also get a graph. A graph is always useful. It's always nice to be able to understand graphical analysis. Basically, this test for equal variances, multiple comparison intervals for the standard deviation. So this is saying, do any of these overlap? If they overlap, say at 7 or 8, which they all do, 7 or 8 is all within the realm of these confidence intervals, then you cannot be 95% confident that they differ because they do overlap. There is a possibility that the variance for northern could be anywhere in here, WTA anywhere in here, so you can't really say that northern is statistically different. Likewise with Pocono and Branson. So this is just another way to analyze the Levine information. They do give the p-value here. So let's move on and learn how to do the hypothesis test. So we're going to do one more time, stat, ANOVA, test of equal variances, response in different columns. We're going to choose the 4 columns in the worksheet. And then we're going to go H0, variances of satisfaction scores are equal across airlines. There's my H0. This is a really important hypothesis. It's our second major hypothesis that we've been learning. So we've got H0, variances of satisfaction scores are equal, variances of satisfaction scores are not equal. I've got an F computed that I'm going to need for this hypothesis test. I get it from my output from the Levine's test. It was 0.71. My F table will have K minus 1 and N minus K degrees of freedom. So that would be 2 and 18 degrees of freedom. My p-value I get from Minitab as well, 0.55. Let's go back and just remember that. So my F computed is 0.71 and my p-value is 0.55, greater than alpha. So my p-value is greater than alpha, which means do not reject. There's not enough evidence to suggest that the variances differ. So there's not enough evidence to suggest that the variances differ means, in effect, that the assumption of equal variances holds. The assumption that we have equal variances hold. Why? Because there's not enough evidence to suggest that they differ statistically. We have to be 95% confident. Good? So that's how we test. That's the first thing that we're learning in today's lecture is how to test for equal variances. So let's go ahead and do another example. So here we have some data on districts. So in this example, we have the number of civil complaints filed against 4 district sheriff's offices during the last 3 months. So in month 1, District 1 had 7 complaints, District 2 had 3, District 4 had 2. In month number 2, blah, blah, blah. So we have a sample of 3 in each district. So we want to check for and do a test for equal variances to make sure that we could do an ANOVA if we were going to. So we're going to put these data into Minitab. Well, it doesn't seem to be copying. So I'm going to go District 1, District 2, and just take a second to do it. All right, so we've got our ANOVA data, right? We're basically would be testing, is there a difference in average complaints across district? But now we're going to just test for equal variances. So we're going to go to stat, ANOVA, test for equal variances. And so response data are in one column for all factor levels. No, they're in multiple. District 1, 2, 3, and 4. And then we just say okay. So stat, ANOVA, test for equal variances. We put in these columns and then just say okay. And here we can see that all of these confidence intervals overlap. The p-value is 0.827. We don't want to keep it, so no, I don't want to keep it. And here is my Levine statistic, 0.3, and my p-value is 0.82, which we'll be using in the hypothesis test that we're going to be doing in just a second. So here is my output one more time. And so we'll go variances in spending are equal, variances in spending, variances in complaints. Isn't it great that I'm doing this? Variances in complaints are equal across districts. Variances are not equal across districts. F computed is 0.3 right there. My F is k minus 1 and n minus k, so 3 and 9 degrees of freedom. P-value is greater than alpha. Here's my p-value. Do not reject. There's not enough evidence to suggest that the variances differ. You can also say T-notes. That's another way I say there's not enough evidence to suggest, is I just write T-notes. And if you just ever turn in anything that says T-notes, it's fine with me too. I know what you mean. There's not enough evidence to suggest that the variances differ. So is this going to be a valid statistical test if we do an ANOVA? Yes, because your p-value is greater than alpha. The variances in effect are not different, which means we can assume that they're equal. Yay! So that's the first thing that we're learning in today's lecture, is how to test the underlying assumption for the one-way ANOVA. So let's do some multiple choice questions. Assume that your p-value is greater than alpha in the test. Average sales are equal across 3 departments. If your p-value is greater than alpha, are you going to reject or do not reject? We're going to do not reject. So it's got to be one of these two. So do we say do not reject, average sales are equal? Or do we say do not reject, there's not enough evidence to suggest average sales are not equal? Yeah, it's this one. It's D. We always have to conclude HA. Either we reject H naught and say, yes, means are definitely not different. The statistics support the fact that the means do differ for sure. 99% confident if the p-value is 0.01. Right? Or you can say, do not reject H naught. There's not enough evidence to suggest means do differ. There's not enough evidence to suggest means differ. We can never say, reject H naught, I am sure means are equal. No, we cannot be sure means are equal. No, we have probability distributions, remember? It's going to be a little high, it's going to be a little low, we're going to have a confidence interval. We can never reject H naught, or we can never do not reject H naught and conclude H naught is true. Never. You always have to have an HA in a statistical conclusion. You always have to have an HA. In every single statistical conclusion that you write, you better have HA. HA is average sales are not equal across departments. That's your HA. You always have to have an HA, whether you reject or do not reject. Okay. An F statistic is ratio of 2 means, ratio of 2 variances, difference between 3 means, and population parameter. F statistic is ratio of 2 variances. Remember, between group variance and within group variance. It's a ratio of these 2 variances. The higher the F computed, the more likely the means differ. How about this one? If your p-value is less than alpha, what does that mean? You reject or do not reject? You reject. Right? P-value less than alpha, if it's a teeny little p-value, then you reject H naught and conclude means differ. All right, p-value less than alpha, reject H naught. Average industries are equal, reject H naught. Average industries are not equal. Which one looks good? We know we reject H naught. Right, it's this one, B. When p-value is less than alpha on a test of equal variances, to check the assumption of the ANOVA. When p-value is less than alpha, the results of the ANOVA are valid, or B. When p-value is less than alpha, the results of the ANOVA are not valid. Which is true, A or B? P-value less than alpha, the results of the ANOVA are not valid. They are not valid. You got to have a p-value greater than alpha because then there's not enough evidence to suggest that variances differ. All right, if p-value is equal to 0.07, this means we will reject H naught when alpha is equal to 0.05. No, p-value is greater than alpha. It would be a do not reject. If your p-value for any hypothesis test is 0.07, this means we will reject H naught when alpha is 0.1. Yeah, that's pretty true. P-value is less than alpha, you reject H naught. So if you only want to be 90% confident, you could use an alpha of 10%, but most people don't. If they're going to spend $1 million, they want to be 99% confident of their result. They don't want to just be 90% confident. All right, how about this one? This means that we can reject H naught with 93% confidence. Yes, 1 minus a p-value is the confidence with which you can reject H naught. So the answer is both B and C are correct. Both B and C are correct. All right, let's keep going. We've got more multiple choice questions here. This is kind of interesting. All right, the output below shows the ANOVA results for a one-way ANOVA that uses data on average number of complaints across 4 different police districts. Managers will spend funds on districts with higher levels of complaints and or may fund a study of best practices for a district that has much lower complaints than another. Using the data below for the 2 key groupings, choose the best recommendation. All right, so here we have the ANOVA for my H naught. Average complaints are equal across 4 districts. Average number of complaints are not equal across districts, H naught, HA. So are they equal or not equal? Means are not equal. At least one mean differs for these districts. Does everybody see that just by looking at the p-value? We really don't even have to look at H naught, HA, F computed, F table statistical result. We can just look at this p-value and say, yeah, means differ for these districts. All right. One district has some hostile sheriffs there, or one district has some super cool copacetic that generates fewer complaints. I don't know. You see what I'm saying? So here we have the ANOVA results, and then here we have the 2 keys. What do we see here with this 2 keys? Let's do an analysis here. What do we see? Which have the highest average complaints? Yep, District 1 and 3 have the highest average complaints, and they're higher than in Districts 2 and 4. But there's not enough evidence to suggest that in the population the means differ. We know that in District 3 the sample mean is higher, but there's not enough evidence to suggest that it's higher in the population as a whole. In contrast, District 3 definitely has higher complaints than Districts 2 and 4, doesn't it? Because it's in a different group. All right, so let's see how we can meld this into something practical. They should spend funds to figure out why District 3 has so many more complaints than District 1. Is that true? Should they spend money to find out why District 3 has so many more complaints than District 1? No, because there's not enough evidence to suggest that they differ. Does everybody see? The fact that they're in the same grouping means that there's not enough evidence to suggest that. Can't be correct. How about this one? They should spend funds to find out why District 3 has so few complaints, and reproduce that in other districts. Why does this district have so few complaints? Now, it looks like the means are higher. That would not be true. How about this one? They should spend funds to reduce District 1 and 3 complaints as compared to other districts. Should they spend money to reduce complaints in District 1 and 3 as compared to others? Yes. So C is correct. Does everybody see how we're making recommendations based upon these Tukey's tests? Very important, very practical. All right, new topic, TwoWayAnova. Instead of just a treatment, now we're going to have a blocking variable. So we've got a treatment group and another way to divide it in order to further explain variation. For a two-factor ANOVA, we test whether there's a significant difference between a treatment effect and whether there's a difference in a blocking effect. So we do have mean square treatment right up here, but we also now have mean square blocks. With a two-way ANOVA, we've got more than just a treatment and a block. If we have more than one observation in each cell, we can also get an interaction. So let's talk about what it is that we can get here. So we have a response variable, right? We have my response variable, very important. But we can do one hypothesis for the treatment effect. And the hypothesis for the treatment effect would be, say, H naught, average drive time, is the same across drivers. So in this example, we've got a two-way ANOVA where we're looking at drive times. So these are different drivers. We've got Piper, Sanders, and McLean. And this is their drive time. When Piper goes on US1, he did it 3 different times. And so they took a sample of his drive times. And when Piper went on US1, it took him 18, 17, and then another time 18 minutes to go from point A to point B. If the route was the west end, then it took Piper 20, 19, and 20. If it were Hickory route, it took him this long in 3 different tries. And if it were Route 59 that he was taking, then in a sample of 3 different times that he was traveling, it took him 22, 21, and 22 minutes. Likewise, we want to know travel times, not just by route, but by driver. So we care how fast is the route, but we're also going to try and explain variation in these times using the driver as well. So one hypothesis is, does average drive time, is it the same across drivers? Another hypothesis would be, does average drive time is the same across routes? So one is the treatment and one is the blocking variable. And it really doesn't matter which one. It might have some theoretical significance, but not in general. It's pretty much 2 one-way ANOVAs. We're going to get an ANOVA table with an F computed for both of these hypotheses and a p-value for both of these hypotheses so that we'll be able to do them. As long as the sample size is greater than 1 in each cell, that is, we just don't have 1 observation in each cell. In this case, we've got 3. As long as the sample size in each cell is greater than 1, then we can get an interaction of the 2 factors, and we'll describe that hypothesis. Kind of to see, hey, does one driver do better on one route than any of the others? So you can kind of separate the effective driver by the route that they're taking. Or you can separate the effective route based upon the particular driver. And so maybe make recommendations like Piper should always go on US1 or something like that. All right, so this guy, the researcher, takes a simple random sample of each drive times. So for example, Piper had drive times like this, this, and this. Now, this is a little different, the way that we have to construct the data in order to put it into Minitab. Because in this case, we do need all the data in 3 different columns. We can't just put it into like we did by columns when we were using the TwoWayAnova. We're going to have to put it in a very specific manner. So we're going to have minutes, which is the outcome measure. So the outcome measure is 18, 17, 18. 18, 17, 18. And the next one, we're going to identify it by either the driver or the route. Does everybody have like binoculars so that they can see these? It's really small. All right, so we've got minutes, and then we've got driver 1 and route 1. So this is going to be route 1, driver 1. Please don't do that. So route 1, driver 1. Now we're going to do driver 2. So next we're going to put in these data. Every single observation has to get put in under the route that they are and the driver that they are. So Sanders, I put these data in, 21, 23, 20. That's going to be driver number 2, but it's still route 1 because we're still US 1. Now McLean, that's 20, 22, 19. That's driver 3, route 1. Next we'll go back up here, 20, 19, 20. That'll be driver 1, but route 2. And then we'll go and do all of route 2. We'll all do, got it? So does everybody see that we have to reconstruct the table in order that Minitab can understand it? So let's go ahead and put these data into Minitab. Let's see. This will work. A time run exception. So what I do sometimes is I'll open up Excel, and it seems to transfer a lot better from Excel into Minitab. And I may need to open up Minitab again. I may have just kept it not functioning for too long. Nope, that worked. So I transferred it from my PowerPoints into Excel, from Excel into Minitab, and that seemed to do much better. All right, so we've got our data in here, and then we're going to go to stat, and this is, it gets kind of complicated. So I'm going to bring this out here, make it a little bigger. So we're going to go to stat, ANOVA, and then we're going to go to general linear model, fit general linear model. And this is our best guess for the TwoWayAnova. This is the most general context, and this is the way we need to do it. In older versions of Minitab, it did have just stat, ANOVA, two-way, not this version. In version 17 and 18, this is a way we're going to run a TwoWayAnova. One more time, stat, ANOVA, general linear model, fit general linear model. Response variable. This is why we have to have it in this format. We have minutes as our response, and then my factors are driver and route. So we're going to go my response, which is minutes, and then my factors are driver and route, my treatment and my blocking variable. In order to get the interaction effect, which we can get as long as we have more than one observation in each cell, we can go to model, interactions through order. So after we do the general linear model, minutes, driver, route, we're going to go to model. And when we do model, we're going to highlight and highlight. Or actually what I'm going to do is I'm going to shift. I'm going to hit the shift key and then highlight both, because we're doing interactions. That is, how does the effective driver affect the route? How does the effective route affect driver? So we're going to add this interaction, and so we're going to add. And then we say, okay. So everybody get that? Let's try that one more time. We're going to go to stat, ANOVA, general linear model, fit general linear model. Put in responsive minutes, factors, driver, route. Next, we go to model. Model, we're going to highlight both. And I do this by highlight, shift, highlight. So now I'm highlighting in interactions, and then I would say add, and it would add a driver by route variable in the model terms. Then you just say OK and OK. And out pops gobs of data. So this is kind of the bottom of it all. But this is what we need. We've got the general linear model, method, values, driver, source, driver. This is the analysis of variance table that provides my F computed for average times H naught. Average times do not differ across drivers. F computed p-value. H naught. Average drive times do not differ across route. F computed p-value. And then we'll come up with our third hypothesis of this interaction. I'll talk to you about that there. So we all know how to get Minitab again? So we put those data in. They've got to be structured perfectly. Every outcome measure has to be associated with particular driver, particular route. And then we're going to go to stat, ANOVA, general linear model, fit, general linear model, model, add the interaction as long as there's more than one observation in each cell. If there's not more than one observation, you cannot do this interaction. You'll just do driver and route. Right, say okay, okay. All right, let's see what we got here. Oh my word, here it is. So this is a way you find the ANOVA table to help answer your questions about the 3 hypothesis tests. H naught, average drive time is equal across drivers. So here's my F computed F table. Here's another, if you want a different perspective on how to do a two-way ANOVA, there's a little blog, Minitab blog, that might help. All right. So here is my analysis of variance table. Let's do 2 hypotheses, one for the treatment group and one for the blocking group. So average drive time is the same across drivers. We've got 3 drivers, so we've got 3 mu's. My F computed, we get straight from here. My So this would be, remember how I said that it's one divided by the other? It would be mean square driver divided by mean square error. 42 divided by 1.13. Right. So this is a 37. Degrees of freedom are kind of the same. Actually, I should write this out. It's going to be equal to F alpha k minus 1, and then the degrees of freedom here are n minus ab, or kb. K is, of course, the number of treatment groups in driver, and b is the number of treatment groups in the blocking variable route. But if you don't know n minus k times b, you can just grab it off of 2 and 24. Those are the degrees of freedom for the error, just like it was before. 2 and 24, you get it right off the ANOVA table. My p-value for this hypothesis is 0, so reject. Average drive time does differ. So one driver may be faster than another. All right, here we go. Average drive time is the same across routes. At least one differs. So here is the hypothesis for route. I got an F computed, an F table with 3 and 24 degrees of freedom. Again, my p-value is 0, so reject. Average drive time differs across routes. So one route turns out to be faster than another or slower than another too. All right. Next, we can do an interaction hypothesis, and this is what this is. This is the interaction that we created in the model statement. And this is the interaction of driver and route to try and explain whether or not there's a difference for one driver that's better in one route, etc. So the exact wording that we use for the interaction hypothesis with a two-way ANOVA is as follows. It says the average travel time by route is not affected by driver. You could also say average travel time by driver is not affected by route. I could switch those. It doesn't matter, one or the other. My alternative is average travel time by route is affected by driver. I've got my computed test statistic right here. My table test statistic is 6 and 24. So that would be equal to F alpha and this would be K minus 1 multiplied by B minus 1 degrees of freedom for that first degrees of freedom. And then this mean square error degrees of freedom are N minus K times B. So K minus 1 is 2 times 3 is 6. If you don't feel like memorizing this, although it is nice to have in case you need to know degrees of freedom at some point for some multiple choice question, I would think you could just look up here, 6 and 24 degrees of freedom in this hypothesis. 6 and 24, that's what you get credit for. You don't actually have to look it up in Google. P-value 0.08, reject. The average travel time by route is affected by driver. Does everybody see how to put the data in, how to have the data, how to put the data in, how to run Minitab, and then how to get the results and then do the hypothesis test? So we know that averages do differ for these, but in terms of the true population, it even differs across the true population. All right, so let's do the Tukey's. Let's get Tukey's results. Because we need Tukey's results in order to do summary and implications, don't we? We need to have a statistical analysis of what mean really is statistically different than another. So we're going to do, to get the Tukey's, in order that we get the summary and implications, stat ANOVA, general linear model, fit general linear model. And then down here, I think what we can get is no, let's see a comparison. So what we're going to do is we're going to go stat ANOVA general linear model. Instead of clicking here like we usually do, we're going to go down to here. Now, you have to have run the general linear model before you can do comparisons, because it's going to be choosing choose terms for comparisons, type of comparisons, Tukey's. We want Tukey's. And we want to choose the items for comparison. So we need to click each one. Click, click, and click. That way you get the comparison levels for each. So you have to do that. And then you say, okay. So let's try that again. We're going to go to stat ANOVA, general linear model, fit general linear model. No! To get summary and recommendations, you have to use comparison. We're going to compare the means in order we can summarize and write recommendations. Comparisons, choose terms for comparison. Yes, driver, click, click. Route, click, click. And driver and route, click, click. So then you say, okay. We can interpret these confidence intervals. Basically, routes 2 versus 3, there's a 0 in it. So they're subtracting the confidence intervals for these routes. So if there's a 0 in it, then the corresponding means are not significantly different. If there's a 0, then they're not significantly different. If there's not a 0, then they are significantly different. So 2 is higher than 1. 3 is higher than 1. 4 is higher than 1. Make sense? I find these graphs, I guess, interesting, but the groupings are so much easier to read. I tend to use the groupings, although it is important that you do understand these graphs. So, is there a difference in driver 2 versus 3? No. Is there a difference between 2 and 1? Yeah. 2 minus 1 is positive. I don't know what that means. We'll just have to see. All right, so this is good. So here's my grouping methods. So this says pairwise. So we got all of this information, and we have pairwise comparisons. So driver 1 is faster than 2 and 3, isn't it? Driver 1 is statistically and significantly faster than drivers 2 and 3. How about by route? Route 1 is across the board statistically and significantly faster than routes 2, 3, and 4. So we can make recommendations. All else equal, we should use route 1, and probably we should use driver 1, right, across the board. So let's see what we did here. All right, here we have all of the summary and stuff that we just got. Summary. Driver 1 is on average faster than others. That's true. Driver 1 is faster than the others. And we would also say there's not enough evidence to suggest that average drive times differ for driver 2 and 3. There's not enough evidence to suggest that average drive times differ, not for the true population. So what would our recommendation be? Use driver 1 over 2 or 3. Don't spend resources to find out if driver 2 versus 3 average times differ. Don't use driver 1 versus 2 because there's not overwhelming evidence to suggest average drive times differ. All right, how about route? Let's do route. Summary, route. Route 1 has faster average drive times than 2, 3, 4. Yep, that's true. Does that make sense? Average 1 has faster drive times. It's in a different group than routes 2, 3, 4. They're all in the same. We can also say there's not enough evidence to suggest that average drive times differ for 2, 3, 4. Right? Not enough evidence to suggest that these drive times differ on average for routes 2, 3, 4. So don't spend resources that assume that there's a difference in average drive times between 2, 3, 4, but do use route 1 rather than 2, 3, 4. All right, I'm back at it. And so what we've got here is that we're making a recommendation for route and driver. And it looks like group F, there's not enough evidence to suggest that among these drivers in these routes that it differs, right? So we probably wouldn't want to choose among one of these 3 and pay 1 more or something like that, right? If we're looking at these combinations among F drivers. So in this case, there's not enough evidence to suggest a difference in the F group. That is combinations 1, 1, 1, 3, 1, 2, and 3, 1. So don't prefer one of these combos to another. On the other hand, it looks like at least combo 1, 1, this guy, is faster than group E. So 1, 1 is faster than group E. 1, 1 is not all of group E, but some of group E. Right? This guy F, 1, 1, is faster than some of group E, these guys. Faster than D group, definitely faster than D group. This guy is faster than C group, B group, and A group. It's kind of hard to describe, but you're going to kind of have to do your best. On a test, I'll try and make it much more straightforward so you can see clearly one versus the other. And we'll do another example here coming up too. All right, let's do another example. It says, show the mini-tab output you get to the following questions. So what we have here is weight loss. So in program 1, males, there's a sample of 3 males, and they lost an average of 23, 21, and 25 pounds. In program 2, males lost an average of 20, 32, and 26. In program 3, males lost an average of 49, 27, and 38. Likewise for females. Here's a sample of females. So we're going to put these data into Minitab and run the regression. So we will put these data into Minitab, not regression, TwoWayAnova, and we'll go stat. We would go stat, ANOVA, general linear model, fit general linear model, and we would put these data into there. And we get information on program number, gender, and then the interaction. So let's do the hypothesis for program. Average weight loss is the same across program. It differs across programs. My F computed, where did I get this 6.01? This is a hypothesis for programs, the type of program that you used, 1, 2, or 3. My F computed is going to be right here. That F value 6.01. My table value is 2 and 12 degrees of freedom. P-value reject. Average weight loss differs across program. So if we were going to do a summary of program, let's remember what the question was. It says run a TwoWayAnova and test weight loss differs by program. So we did that hypothesis. Now what we need to do is we need to make summary and recommendations for both program and gender. All right, summary. Which is the best program? Program 3 has higher weight loss than program 1 or 2. There's not enough evidence to suggest that there's a difference in weight loss between programs 1 and 2. Recommendation, use program 3 rather than 1 or 2. Use program 3 rather than 1 or 2. It's higher weight loss for the population as a whole. And then the other recommendation is don't spend more money to attend program 1 versus 2. Don't spend more money. All right, and then next wise, here we have for gender. Here's our Tukey's results for gender. Mean males versus females. What can we say? There's not overwhelming evidence to suggest that there's a difference in weight loss between males versus females. Recommendation, don't spend resource selling to men versus women for greater weight loss, promoting greater weight loss. All right, so here we go. We know about the F distribution, how to look up critical values in Google, TwoWayAnova. What did we do today? We did the 2 hypotheses for the TwoWayAnova, an interaction. If there's more than one observation in each treatment and block group, then we can do an interaction hypothesis and then how to write summary and recommendations. There is one more multiple choice question with answers. I will let you explore that on your own. So what's next? What's next? You have homework 2 for practice for the TwoWayAnova, and then also quiz 1 and quiz 2 are due September 3rd. But we've got 2 weeks, so we've got 2 Wednesdays coming up. So feel free to come in and speak with me about anything that might be confusing.